Greetings, Assalamualaikum and good day to distinguished judges and fellow innovators. I am Muhammad Irfan Ekal and I am honored to present our research titled Toward Greener Energy Storage Tapioca Starch as a Natural Binding Alternative to Synthetic Polymers in Water-in-Salt-Based Supercapacitors. This project was done in collaboration with my team members, Jacqueline Jubilee, Dr. Siti Nurfadila and under the supervision of TS Dr. Fahmi Yan Yan. We are from the Faculty of Engineering, University Malaysia Sabah. First, let me begin by giving a bit of background on why this research is important. Today, our world is facing a growing demand for reliable and sustainable energy. To address this, there has been a global shift toward renewable energy sources like solar, hydro, and wind power. These sources are clean, abundant, and environmental friendly. However, there is one single challenge, which is instability from often intermittent and fluctuating. This is where energy storage system or ESS plays a crucial role. Our research focuses on one type of ESS, which is known as supercapacitor. So, what exactly is a supercapacitor, and how does it compare to the traditional battery? A lithium-ion battery stores energy chemically through redox reaction, and it offers higher energy density. However, it generally has low power density, so it takes time to charge and discharge. While on the other hand, a supercapacitor stores energy physically through electrostatic charge accumulation. This gives it a very high power density, and however, it has a very low energy density compared to battery like ion. So it stores less energy than a battery of the same size. In our study, we focus on improving the performance and sustainability of supercapacitors by developing greener materials, which I will explain further in the next part of this presentation. This type of supercapacitor consists of three main components, which is symmetric electrodes, separator, and also electrolyte. The electrolyte is dropped onto the separator, allowing ions to move between the electrodes and enabling charge storage. So, let's begin with the main problem our research aims to solve. First, let's talk about the electrolyte. Flammable organic electrolytes are widely used because they offer a wide electrochemical potential window which helps increase energy storage. However, they are also highly volatile and toxic, making them a fire hazard, especially under high temperature or high voltage conditions. On the other hand, aqueous electrolytes are safer and more stable in ambient condition. However, they suffer from a narrow voltage window which limits their energy density. Meanwhile, ionic liquids, which are also stable and high performing, are often very expensive and not scalable. Second, we have the issue of synthetic binders, particularly PVDF. PVDF is widely used commercially, but it requires the use of NMP, and due to its health and environmental risk, NMP is now regulated in the EU and US, which raises concerns for large-scale manufacturing. So, this led us to an important question. Can we develop a greener, safer, and more sustainable supercapacitor without compromising on performance? This question became the foundation of our study and led to the innovation we are presenting today. In our study, we proposed Tapioca Starch as a green, sustainable alternative to synthetic binders like PVDF as the first innovation. Why Tapioca Starch? Because starch-based binders are known for their strong cohesion and film-forming properties, and they work well in both aqueous and organic electrolyte systems. Tapioca Starch is also derived from the cassava plant, which is naturally abundant and widely cultivated, especially in Asia. This makes it a strong candidate for green supercapacitor development. Next, let's talk about the electrolyte, another key innovation in our supercapacitor design. We use a water-in-salt electrolyte sodium nitrate NaNO3. This system offers a high electrochemical stability window up to 2.2 volt under ambient condition. This is a significant improvement compared to conventional aqueous electrolytes. It is also neutral in pH and is the most cost-effective option, making it viable for scalable application. It also has an excellent balance of safety, performance, and affordability, all while supporting sustainable development. In this study, we also use NIO in addition with AC, and it became a hybrid supercapacitor. The reason why we use NIO is because it has a high theoretical capacitance value for up to 2584 Fg. Now, moving on to the result of our ACI morphology of NIO AC composite. On the left side, we see NIO AC Tapioca Starch. It has a slight surface cracks due to the natural water-based nature. However, it still maintains good porosity and ion transport. In the middle one is NIO AC PVDF. It has a smooth and well-packed surface. This supports high electrochemical performance. And meanwhile, lastly is NIO AC PTFE. It has compact and dense surface, which may hinder ion diffusion and limit performance. Now, moving on to the result of our study of electrochemical analysis. We synthesized NIO and AC composite and tested it using PVDF, PTFE, and our proposed Tapioca starch. From our analysis, we found that NIO calcine at 500 degrees Celsius labeled as NC513500 gave the most optimal performance. It showed the highest specific capacitance, the lowest ion drop, and also the smallest semi-cycle in EIS, which means lower internal resistance and better ion transport. This confirms that 500 degrees Celsius is the ideal calcination temperature for NIO to achieve strong synergy with AC, resulting in enhanced supercapacitor performance. This slide shows cyclic voltammetry CVA result at 50 MVS for different binders in two systems. For the left side is AC-only electrodes, and on the right side is NIO-AC composite electrodes. And the key findings are PVDF gives the highest specific capacitance in both systems, consistent with its strong performance as a commercial binder. Meanwhile, for Tapioca Starch, it performs well with the AC-only electrodes but shows a slight drop with NIO. Still, it maintains good stability and conductivity, making it a promising eco-friendly low-cost alternative. And lastly, PTFE has the lowest performance in both cases, likely due to weak contact and poor ion transport. Next, this slide shows the galvanostatic charge-discharge GCD curves at 0.5 Ag, highlighting the internal resistance IR drop for different binders. The key points are PVDF shows the lowest IR drop, confirming its strong conductivity and interfacial stability. Adding NIO reduces the IR drop for all binders, improving overall charge transport. For Tapioca Starch TS, capacitance slightly dropped with NIO as seen in CV. However, in IR drop, it has improved significantly from 0.24 volt to 0.15 volt. This shows TS plus NIO enhances GCD performance and maintains electrical stability. PTFE still had the highest IR drop even with NIO, indicating poor conductivity. Next, this slide shows EIC result to evaluate internal resistance and ion transport. The key observations are a smaller semicircle in the high frequency region means better charge transfer. Adding an ion reduces semicircle size for all binders, indicating improved conductivity. For TS, the NIO AC TS composite shows much better performance than AC only TS, confirming that NIO enhances the electrochemical interface. PVDF still has the smaller semicircle, showing the best conductivity. Meanwhile, PTFE shows the largest semicircle, meaning that it has the highest resistance. In this next slide, we compare energy and power density for different binder systems using a Raygun plot. The key highlights are PVDF still performs best with the highest energy and power densities, thanks to its excellent electrochemical and structural properties. Meanwhile, for TS, it shows a clear improvement when combined with NIO. The NIO-AC TS electrode, which is NC500TS, outperforms the AC-only TS, showing higher energy and better power delivery. This proved TS works better with NIO, making it a more competitive and sustainable binder option. PTFE again shows the lowest performance in both energy and power density. The plot also emphasizes the role of NIO AC composite, which NIO enhances performance across all binders, and NIO calcium at 500 degrees Celsius give the best results, making it the ideal condition. Next slide is market potential for green energy storage. The global energy storage market is growing fast and is expected to hit USD 31.72 billion by 2033. This growth is driven by clean energy needs in EVs, solar, and electronics. This opens up big opportunities for green supercapacitors. Our solution supports this trend, which is we use Tapioca Starch as a natural binder and wise electrolyte safe and non-toxic. It also avoids harmful chemicals and uses low-cost, eco-friendly materials. In short, our system is green, safe, and ready for the future energy market. Moving on to the status of innovation, current phase, and readiness. Our project is now between phase 3 and phase 4 of development. We have tested the concept in the lab using coin cell prototypes, and it includes Tapioca Starch binder, NIO-AC electrodes, and a safe, wise electrolyte. We have built a working small-scale prototype CR2032 with stable performance. Now we are ready to share it with industry partners for future scale-up and real-world use. Lastly, innovation of this work. Our project improves supercapacitors in a greener, safer way. The key innovations are safer electrolyte system. We use a high concentration nitrate-based wires that works up to 2.2 volt. It is more stable and less dangerous than traditional electrolytes. It is also eco-friendly materials, which we use non-toxic sodium nitrate and avoid harmful solvents. It is also safer for people and the environment. Third is natural binder. We replace synthetic binders with Tapioca Starch, a biodegradable and low-cost option. This allows cleaner, safer electrode production. And lastly, support global sustainability goals. It helps achieve SDG 7 clean energy and SDG 13 climate action. In short, a green supercapacitor system that boosts performance while protecting the planet. These are the list of the references that we use for this project. That will be all for this presentation. Thank you for your time and attention. Thank you.